if you're listening to this, chances are you already know the exact feeling I'm about to describe.
Oh, I bet they do.
Right. You've been tinkering with an AI agent. Maybe you strung together a few carefully crafted instructions. You added a tool call so it could search a database, and suddenly it works.
Just like that.
Exactly. Yeah. The model actually executes the task. It pulls the data, it formats the response perfectly, and you get that initial, undeniable thrill of invention. It feels like magic.
It really does, on day one at least.
Yeah, exactly, on day one.
Yeah.
But anyone who has actually built these systems knows the absolute dread of what happens next.
Yeah.
Because what happens on day two?
Day two is when reality hits.
You take that beautiful, fragile agent and you put it into a real high-volume workflow. And almost immediately, the magic just starts to crack.
Oh, completely shatters.
Costs inexplicably drift upward. The latency stretches out from, I don't know, 2 seconds to 15 seconds.
Yeah.
And your users are just staring at a loading spinner.
Which nobody wants.
Right. A tool call that like perfectly yesterday suddenly fails today because the input data shifted slightly. Mm-hmm. You try to fix one component with a tiny text edit, and somehow completely unrelated parts of the system just shatter.
Yeah, it is the classic painful transition from a controlled demo to a live production system.
Yeah.
The entire landscape of the engineering problem just changes overnight. You know, you are no longer building a prototype. You are trying to stabilize a chaotic, probabilistic engine.
And that shift from invention to stabilization, that is the entire focus of our deep dive today.
It's such a necessary shift, too.
So necessary. We're pulling our insights today from rooted layers. Specifically, this incredibly detailed piece they published recently that is entirely grounded in AI research and actual operational realities.
Yeah, the post is really phenomenal.
It really is. So we're going to treat this deep dive a bit like two researchers just thinking out loud in the lab. We want to be curious, calm, and really driven by the concrete insights in the post.
No hype, just the actual mechanics.
Exactly. Our mission is to unpack the key ideas, the mental models, and the bigger patterns behind what Rooted Layers calls the optimization and self-improvement of AI workflows.
Because that first working agent is really only the beginning.
Right. Once you actually have a workflow in place, your main problem is no longer invention. Your main problem shifts entirely to improvement.
Yeah, and a useful way to think about this is that in production, systems naturally degrade. I mean, they just do.
They rot.
Exactly. Prompts regress as models are quietly updated behind APIs. The data environment changes. If you do not have a rigorous mental model for how to apply improvement pressure to a live workflow...
Which most people don't.
Right, they don't. And if you don't, your system will eventually collapse under its own weight. Or at the very least, it's going to become far too expensive and slow to justify its existence to your finance department.
Which is usually what kills it.
Yep. So when you talk about improvement today, we're not talking about casually rewriting a sentence because you had a clever idea over coffee. We are talking about systematic, algorithmic optimization.
Okay, let's unpack this. We need to start with the first major paradigm shift that the post introduces. The real practical value of the chapters we're analyzing today is that they move the optimization target away from the single prompt.
Thank goodness.
I know, right? Away from the single prompt and onto the whole workflow. They argue explicitly that this is the only correct frame for agent engineering.
It absolutely is.
But to really grasp why that matters, we have to look at why the old way, the way most people still build AI, is fundamentally broken for production.
Yeah, because the old way is just a direct holdover from how we all first interacted with large language models.
The chat box.
Exactly. We started with a chat box. You put text in, you got text out. Naturally, when things didn't work, what did you do? You changed the text you put in, you tweaked the prompt.
You added things like, think step by step.
Right. Or you wrote this massive, dense paragraph of highly specific constraints, hoping the model would adhere to them. And that worked fine for a single, isolated generation.
But a production AI agent is rarely a single text box anymore.
Almost never. It is a sequence of interconnected events. It's a multi-step process. A routing agent might plan a task, hand it off to a retrieval tool to fetch documents, summarize that retrieved data, pass that summary to another agent for formatting.
And then validate the final output against a schema.
Exactly.
The analogy that always comes to mind for me here is a sprawling physical factory.
Oh, I like that.
Yeah, imagine you own this massive manufacturing plant with an intricate assembly line. Raw materials come in at one end, They pass through dozens of machines, conveyor belts, specialized workstations, and a finished car rolls out the other end.
Okay.
Now imagine a car comes out with a badly dented door. The old way, that single prompt tweaking method we used to do, is like walking onto that massive factory floor, finding one specific worker somewhere in the middle of the line, and just yelling new instructions at them over and over again.
Hold the wrench differently.
Be more careful.
Right.
You might make that one worker slightly better at their specific motion, but you have no idea if the dent is actually happening because the conveyor belt before them is moving too fast.
Or if the raw steel they received from the previous station was flawed to begin with.
Exactly. You are applying intense pressure to a tiny, isolated component without understanding the factory floor.
That is a highly accurate way to visualize it. You're trying to optimize a complex interconnected system by treating it like a single, isolated black box. And the post argues that we have to fundamentally change our perspective.
We have to stop viewing our AI system as this mystical exercise in prompt craft.
Yes, stop being prompt whisperers.
Right, and start viewing it as a programmable object. It's a workflow. And workflows have distinct measurable properties.
They have nodes, which might be individual model calls. They have edges, the routing logic moving data between those nodes.
They have strict input and output schemas defining what data is even allowed to pass through.
And tool execution behaviors. When you look at the system through that engineering lens, you realize that endless manual text tweaking is actually the least sophisticated, least effective way to improve the system.
Which brings us to a highly practical question for you, the listener. Once the system actually works, where exactly should improvement pressure be applied?
Right. If we aren't yelling at the single worker on the assembly line, what are we doing?
Right. What are our actual options? The post identifies 4 specific levers we can pull. First, there's prompt improvement, which still exists, but we'll see it operates in a vastly different context now.
Very different.
Second, there's workflow topology improvement, which essentially means changing the actual shape and layout of our factory line.
The architecture itself.
Right. Third, there is tool use improvement. And fourth, there are feedback loops that improve the system either dynamically during a run or passively between runs.
Having that precise categorization is just incredibly clarifying for an engineering team. It stops you from blindly guessing. By breaking the system down into those 4 distinct levers, you can begin to isolate and measure where the actual bottleneck is located.
Are we failing because the extraction node doesn't understand the input format?
That's lever 1.
Are we failing because we're asking a single node to do too many complex reasoning tasks at once, and it needs to be split into 2 separate, simpler steps?
That's lever 2, topology.
Are we failing because the database query keeps returning irrelevant garbage?
Lever 3, tool use. This structured diagnostic approach is really the dividing line between amateur tinkering and professional agent engineering.
I want to transition into our deep dive of the actual literature now, because the post doesn't just theorize about these 4 levers. It actually roots them in specific groundbreaking research papers.
Yeah, papers that chart the evolution of how the industry is actively solving these exact bottlenecks.
Yeah.
And this fits a broader pattern we're seeing across the entire field right now. We are transitioning away from manual, human-driven tweaking and moving toward automated, systematic, algorithmic optimization.
Using AI to optimize AI.
Exactly. We are increasingly using the models themselves to optimize the architecture of the systems they operate within.
So let's start with that first lever,
Right.
prompt improvement, but doing it the automated way. The material highlights a paper called OPRO, which stands for Large Language Models as Optimizers.
Right.
The core concept here completely reframes prompt writing. It moves it away from human craft and turns it into an iterative optimization function.
OPRO is fascinating because it directly tackles that exhaustion we just discussed. Human engineers get tired of guessing which arbitrary combination of verbs and adjectives will make a model behave reliably.
Please be a helpful assistant versus you are an expert data analyst.
Exactly. It's exhausting. OPRO proposes a different path. It uses a model to generate dozens of variations of a prompt. Then, it programmatically tests those variations against a defined set of evaluation cases, a test suite. It scores the outputs, identifies which prompt variations yielded the highest accuracy, and then this is the cool part. It asks the model to generate a new batch of prompts based specifically on the structural traits of the most successful previous attempts.
Wow.
It is essentially an evolutionary algorithm, but applied to natural language instructions rather than code parameters.
The implications of OPRO are fascinating.
Yeah,
It fundamentally shifts the job description of a prompt engineer from writer to evaluator.
exactly.
But I have a really practical concern here. If OPRO is just generating dozens of variations and running them against a massive test suite over and over, isn't that incredibly expensive?
Oh, very.
How does an average startup afford to burn thousands of tokens just guessing prompts?
That is the exact right question to ask, and it highlights a crucial limitation. OPRO is not a tool you run constantly on every node in your system. The post is very specific about when to deploy this.
When do you use it?
You use OPRO when prompt comprehension is the proven bottleneck of a specific node, and crucially, when you have strictly measurable outputs. You have to be able to mathematically or programmatically score the local node's weakness. The high upfront compute cost of running OPRO is an investment. You pay that compute cost once in your development environment to find a mathematically superior prompt.
And then that saves you money in production because the node fails far less often, so you have fewer retries.
Precisely. But you cannot run OPRO if it doesn't know what good looks like. If you cannot programmatically state, attempt A scored an 80, attempt B scored a 90, then OPRO has no evolutionary fitness function to optimize toward.
Right, it's just guessing blindly. That makes the requirement for measurable outputs absolutely non-negotiable.
Yep.
Now, moving up the complexity scale, the material brings us to a paper called TextGrad, Automatic Differentiation via Text.
Yeah, quite a title.
I'll admit the title sounds a bit intimidating, but the concept is brilliant. It takes the idea of programmatic feedback and generalizes it into textual gradients. Let's unpack what that actually means.
To understand TextGrad, we have to borrow a fundamental concept from traditional machine learning gradients. In training a standard neural network, a gradient is essentially a mathematical arrow pointing in the direction of lower error. It tells the system mathematically how to adjust its internal weights to get a slightly better result next time.
Like pointing down the hill toward the right answer.
Exactly. TextGrad takes that deeply mathematical concept and forces it into the realm of natural language.
How so?
It generates structured textual critique that acts exactly like a gradient. It tells the preceding node not just that it failed, but in what specific direction it needs to alter its textual output to succeed.
Wait, what does a textual gradient actually look like in plain English? Like, if I have a workflow where step 1 is extracting financial data from a messy PDF, and step 2 is formatting it into a clean markdown table, and the table comes out broken.
Okay.
What exact text is TextGrad passing backward?
In that scenario, instead of simply passing back a generic error like formatting failed,
Which isn't helpful.
right, TextGrad would generate a highly specific critique that reads something like, the output from step 1 provided dates in a mix of written formats like October 4th and numeric formats like 104. This inconsistency caused the markdown parser in step 2 to fail.
Oh, wow.
To resolve this, step 1 must convert all extracted dates to the strict ISO 86601 format, such as YY, YYY, and MDD, before passing the data forward. That critique is the textual gradient.
That is incredibly specific. It provides the exact directional adjustment needed.
Exactly.
So instead of a simple pass-fail, it treats a multi-step textual system as a true optimization object where feedback can actually propagate backward through the chain.
Yeah, because workflows are deeply interconnected. If step 3 in your workflow fails, the root cause might actually be a slightly ambiguous but technically correct output from step 1.
Right.
TextGrad is incredibly useful when you need to turn vague failures into highly structured, actionable optimization feedback that improves the whole chain, not just the final output node.
That is a massive leap forward in automated diagnostics.
It really is.
But the material also grounds us by pointing out that sometimes you don't need heavy, complex optimization algorithms passing gradients backward.
No, sometimes that's overkill.
Right. Sometimes you need a much lighter touch. That brings us to 3 papers grouped together in the research: Self-Affine, Reflection, and Voyager.
Yes.
These represent lighter weight self-improvement paths. Let's break down how they differ.
Well, these 3 papers are variations on a single theme, using feedback to improve performance without fundamentally changing the architecture of the system.
Okay.
Self-Refine is the most immediate and localized. A node generates an output, immediately looks at its own output, critiques it against its given constraints, and generates a corrected version before finalizing the step.
It improves outputs purely through self-critique within a single active run.
Exactly.
It's essentially like writing a rough draft of an email, reading it over to catch typos or tone issues, and fixing them before you hit send.
That's a perfect parallel. Reflection, however, takes it a step further.
How so?
Reflection operates across multiple runs over time. If an agent tries to complete a complex task and ultimately fails, it pauses to analyze the failure path. It writes a structured lesson learned about why it failed.
Like, I used the wrong search term in the database.
Yes, exactly. And it stores that lesson in a persistent memory retrieval system. The next time it faces a similar task, it searches its memory, retrieves that specific lesson, and actively avoids making the same mistake.
So it's improving its future attempts through stored, localized lessons.
Right.
And then there's Voyager, which made huge waves when it was published because the researchers applied it to an agent playing the video game Minecraft.
Oh, Voyager is a brilliant extension of these concepts. It improves future behavior by building a permanent skill library.
Skill library.
Yeah. As the agent stumbles around and eventually figures out how to execute a complex sequence of actions like mining diamond in Minecraft, which requires crafting specific tools first.
Right, you need the iron pickaxe first.
Exactly. It writes that successful sequence into executable code and saves it to a library as a reusable skill.
That's amazing.
Over time, its library of executable skills grows, allowing it to tackle increasingly complex challenges without having to relearn the foundational steps every single time.
So if we translate Voyager from Minecraft into an enterprise setting,
Yeah.
it's like an AI customer support agent figuring out the exact sequence of API calls needed to process a refund for a specific type of legacy account.
Yes.
Saving that sequence and then just deploying that refund skill instantly the next time it encounters that account type.
Precisely. And the research gives clear guidance on when these lightweight methods are appropriate. They are best for repeated near-miss failures. They offer relatively cheap, feedback-driven improvement.
Near-miss failures, okay.
Yeah, if your agent almost gets the right answer but consistently misses a small formatting constraint, Self-Refine can catch that. If it keeps falling into the same logical trap on a specific type of query, Reflection's memory can steer it clear.
I see the immense value there. But my concern is the cost in terms of latency.
Oh, absolutely.
Like if I implement Self-Refine, I am effectively asking the model to process the prompt, generate an answer, process its own answer, generate a critique, process the critique, and generate a final answer.
Yeah, you're doubling or tripling the work.
My user is sitting there waiting 3 times as long for a response.
And your concern is the exact reason these techniques must be applied surgically. Every time you ask a model to critique itself, you are burning tokens and adding seconds to the response time.
You must justify that severe latency tax with a measurable, necessary increase in task quality.
Exactly. Furthermore, there is an even deeper risk, and it is a common pitfall for teams adopting these self-correction methods too quickly. The material heavily warns about the danger of weak critique signals.
What actually happens when the critique signal is weak?
If the model's ability to evaluate its own work is flawed, if its internal compass of what is correct is slightly misaligned with your business logic, then looping it through self-refine or reflection will actually cause it to confidently drift further away from the desired outcome.
Oh, no.
Yeah, it will look at a correct answer, falsely critique it as incorrect based on a hallucinated rule, and refine it into garbage. You are effectively automating the amplification of its own blind spots.
A system confidently optimizing itself in the wrong direction.
Exactly.
That is a terrifying thought for anyone managing a production environment.
Which is why the implementation of these loops requires external objective measurement, which is the foundational theme we are building toward.
Right. But before we get to measurement, we have to talk about the final pair of papers in this section of the research, because here's where it gets really interesting.
It really does.
We've talked about optimizing the specific text instructions, and we've talked about catching errors in the outputs. But what about optimizing the layout of the factory floor itself?
The architecture.
Right. The post brings up AFlow automating agentic workflow generation and GPT-Swarm.
This represents the current frontier of agent engineering. Both AFlow and GPT-Swarm fundamentally challenge the traditional assumption that a human software engineer should be the one manually designing the workflow diagram.
They treat the workflow structure itself, the topology, as a searchable, optimizable parameter.
Yes.
So if I have manually built a linear workflow that goes plan task,
Yes.
then retrieve data, then write draft, then review draft.
A standard linear chain.
Right. AFlow might analyze the performance data over 1,000 runs and decide, actually, you are getting terrible results because you are retrieving irrelevant data. You need a validation node inserted before the retrieval node to clean the search queries.
Exactly.
And it will literally rewrite the Python code of the workflow to physically insert that new node and reroute the edges. It rearranges its own architecture.
Yes. And GPT-Swarm pushes this concept even further away from linear chains and into complex graph-shaped workflows. Yeah. It optimizes how different agents within a swarm communicate, how they vote on answers, and how they route subtasks among themselves based on their specific strength.
Wow.
It is a profound architectural shift. The system is no longer just optimizing the instructions given to the individual workers. It is actively knocking down walls and building new conveyor belts to maximize throughput and quality.
I'm just imagining the compute required for that. If an algorithm is running hundreds of multi-agent configurations, testing different topologies, isn't that computationally massive?
It is incredibly heavy, which is why the research comes with a massive glaring warning label. Do not start here if your baseline system is unstable.
Don't start with a sledgehammer.
Exactly. The distinct risks are premature complexity and noisy search spaces. Think about it. If your fundamental extraction prompts are garbage, or your input schemas are broken,
Allowing an AI to endlessly search for better topologies is like trying to fix a crumbling foundation by rearranging the furniture on the top floor.
that is exactly what it is. The mathematical search space for possible workflow topologies is vast. If the underlying nodes are failing randomly, the performance signals the AFlow system receives will be pure noise.
It'll just generate spaghetti.
It will generate incredibly complex, sprawling, expensive workflows trying to route around basic prompt errors. You only escalate to topology optimization when the foundational nodes are rock solid.
That perfectly bridges the gap to the next crucial topic. We've covered this arsenal of levers, from OPRO fixing prompts to AFlow rewriting architectures. But none of this works. Not evolutionary prompts, not textual gradients, not topology search, unless the system has an infallible way to measure success.
Measurement is everything.
That brings us to Section 3, the measurement mandate and the massive rise of LLMs as judges.
This is perhaps the single most crucial mindset shift required for anyone moving an agent out of a playground and into production. The material explicitly references Empty Bench and Chatbot Arena. Now, most people in the industry know these as popular public leaderboards, where you can check if the newest Claude model is currently beating the newest GPT model.
Right, the bragging rights boards.
Exactly. But the post argues that their true historical importance isn't the leaderboard itself, it is the underlying methodology. Those projects normalized and validated the concept of LLM as judge evaluation.
Let's contextualize why that was so necessary. If you were going to run an optimization loop like OPRO, where you test 100 different prompt variations,
Or AFlow, testing 50 architectures.
right, you need to rigorously score the results of every single one of those thousands of test runs. Historically, scoring complex, open-ended textual output required human beings. You had to sit a domain expert down with a spreadsheet and have them read the outputs and rate them on a scale of 1 to 5.
And relying on human evaluation simply does not scale in an automated engineering pipeline.
It just doesn't.
If human review is required for every experimental tweak, your iteration cycle goes from seconds to weeks. The financial cost becomes astronomical.
Yeah.
You cannot run an automated optimization algorithm if the algorithm has to pause for 3 days waiting for a human review board to grade its latest attempt. Agent workflows desperately need high-velocity, programmatic judgment, and scoring loops.
The solution is to use a highly capable model to judge the output of our workflow. It's drastically cheaper, it evaluates in milliseconds, and it scales infinitely. But we're essentially using an AI to grade an AI's homework.
Yes, we are.
The material clearly points out the inherent risks here, noting significant calibration errors and blind spots.
This raises an important question. How do you trust the judge? We know that models have documented formatting quirks and stylistic preferences when acting as judges. Well, for example, they often display a strong preference for verbosity. If you give an LLM judge 2 answers, one is a concise, perfectly accurate 10-word sentence, and the other is a sprawling 500-word essay that contains the correct answer buried in fluff.
The judge likes the essay better.
Almost always, the LLM judge will frequently score the 500-word essay higher simply because it looks more comprehensive.
Wow.
They can also suffer from position bias, where they arbitrarily favor the first option presented to them in a side-by-side comparison, regardless of merit.
It's exactly like a high school student realizing that a specific teacher gives higher grades to essays that use big, complicated words, regardless of the actual argument.
Exactly.
The student stops trying to make a good point and just starts using a thesaurus to write verbose nonsense.
Yeah.
If you deploy an LLM as judge without addressing these blind spots, your optimization loops like OPRO or AFlow will mercilessly optimize for the judge's stylistic quirks, not for actual ground truth quality.
And when that happens, you experience the terror of the system drifting.
Drifting.
Yeah, you might run a massive computationally expensive optimization pass over the weekend. You come in on Monday, high-five your team because your automated LLM judge scores just went up 20%.
And you push the new prompts to production.
And an hour later, customer complaints start rolling in because the agent is now generating massive walls of text that confuse the users.
Which brings us to a standout quote from the rooted layers analysis. And this is a concept that every listener should write on a sticky note and stick directly to their monitor. An optimization process without regression checks is a drift generator.
A drift generator. It is an entirely accurate, chilling phrase.
It really is.
If you are constantly tweaking prompts, changing data schemas, and adding self-reflection loops without a rigid, unchanging baseline to test against, you aren't actually optimizing, you are just drifting.
You're just wandering.
Exactly. You might fix one specific edge case mug, but you introduce two massive regressions elsewhere without realizing it because you aren't checking. You are wandering blindly through a multidimensional configuration space.
Okay, so we know the theoretical tools, we understand the literature, and we recognize the terrifying reality of becoming a drift generator if we don't measure correctly.
Yes.
This is the perfect pivot point in our deep dive. The material doesn't just leave us with academic warnings. It provides a highly specific, highly actionable operational roadmap.
The blueprint.
Exactly. Section 4. The default optimization blueprint. This is the practical how-to for the listener. The post lays out a recommended 6-step build order for optimizing an AI production system.
And the sequence is not arbitrary. It is forged from the pain of countless failed production deployments.
Lots of scars.
Lots of scars. It heavily prioritizes architectural stability over algorithmic complexity, and it demands you exhaust cheap fixes before you ever attempt expensive architecture searches.
I want to spend significant time here walking through this step by step. Step 1, lock an evaluation set. The material says to freeze it. Define your representative tasks before you tune a single parameter.
This is your primary defense mechanism against becoming a drift generator. Before you change a single comma in your extraction prompt, you must build a comprehensive test suite. You need a diverse collection of representative tasks, historical inputs paired with their expected ideal outputs or strict success criteria.
And then you lock it.
You place it under version control and you do not change it. The post is adamant. If the system cannot be evaluated repeatedly against a stable set of examples, any optimization you attempt is mostly noise.
Right.
You are trying to measure the wind, not the performance of the engine.
The analogy I use here is trying to track your weight loss on a broken scale that gives a completely random number between 150 and 200 every time you step on it.
Oh, that's good.
You can change your diet all you want, but you have no idea if the diet is actually working because the measurement tool is fundamentally unstable.
Exactly.
So step 1 is buying a calibrated scale. Lock the evil set. That brings us to step 2. Measure the current system. The blueprint lists specific, required optimization metrics. Task quality, pass rate, tool invocation accuracy, retrieval quality, latency cost, stability across runs, and regression rate.
Notice the immense breadth of those metrics.
Yeah, that's a lot more than just did it work.
Right. In the prototype phase, developers only care about one metric. Did it get the right answer? But in production, task quality is just one dial on a massive dashboard.
Right.
A model that achieves a perfect 99% pass rate but takes 45 seconds to respond and costs $4 per user query is a catastrophic failure in almost every business context.
No one will use it.
No one. Optimization must begin with comprehensive measurement, not with editing. You have to establish your exact baseline across all these dimensions, speed, cost, and quality, before you try to improve anything.
Let's ground this. Imagine we're building an automated customer support routing agent. Step 1, we gathered 500 historical customer emails and locked in the correct department they should be routed to.
Okay, that's our evil set.
Step 2, we run our agent against those 500 emails and measure the baseline. We find it gets the routing right 70% of the time, takes 3 seconds, and costs 2 cents per email.
We have our miserable but accurate baseline.
Exactly. Now we want to fix it. Step 3, Improve the cheapest surfaces first. The blueprint lists these explicitly. Output schemas, prompt clarity, retrieval configuration, tool descriptions, and retree stop policies.
What is fascinating here is what is deliberately not on this list.
Right.
Notice that re-architecting the workflow or deploying self-refining loops is entirely absent from step 3. The blueprint forces you to pick the absolute lowest hanging fruit.
Was it?
Because these are the highest leverage, lowest risk changes you can possibly make.
Let's talk about why these are so high leverage. I want to dive deep into something like output schemas or tool descriptions, because a lot of people think the AI is failing because it's not smart enough.
Often, an agent fails not because it lacks the necessary reasoning capabilities, but because the boundaries and formatting of the task are poorly defined by the developer.
Interesting.
Let's take output schemas. If you ask a model to extract a date and you just use free text, please provide the date, it might output next Tuesday or October 4th or the 4th of October.
And the downstream software expecting a date variable just crashes.
Exactly. But if you implement a strict JSON schema, which is just a standardized machine-readable data format, and you enforce that the output must strictly match the ISO 8601 standard, which looks like YMMDD.
You instantly eliminate entire categories of parsing errors.
Yes. Or looking at tool descriptions.
Yeah, let's talk about those.
Tool descriptions are essentially the prompts for the agent's hands.
I like that phrase.
If your tool description just says search database, the agent has to guess what parameters to use. If you rewrite that description to say, search the customer database using a valid email address string to return a JSON array of the last 5 purchase histories.
The agent suddenly knows exactly how, when, and why to use that tool.
Precisely. These are incredibly cheap changes. They take an engineer 20 minutes to write, they cost 0 additional compute tokens during runtime, they add 0 latency, and they can dramatically reduce the error rate.
It makes total sense. You have to fix the simple misunderstandings and formatting issues before you hire a complex algorithmic manager to oversee the work.
Exactly.
But let's say we've done that. The prompts are crystal clear, the JSON schemas are bulletproof, the tool descriptions are highly specific, but the agent still occasionally fumbles the complex logic required for certain edge cases.
That leads us down the blueprint to step 4.
Right. Step 4, add feedback loops.
Here is where you finally introduce the techniques from the research papers we discussed earlier. Self-refinement, programmatic critique, or memory-backed reflection like reflection.
But the blueprint adds a crucial non-negotiable condition. You only introduce these loops where there is empirical evidence from your measurements that they will reduce repeated systemic failures.
Yes. Evidence is key here.
I want to push on this. You don't just sprinkle reflection over the whole workflow like magic optimization dust because you read a cool paper about it.
No, absolutely not. You look at your dashboard from step 2, you identify a specific routing node that keeps missing near-miss logic failures, and you apply the feedback loop locally to that exact bottleneck.
Because, as we calculated earlier, adding these loops introduces a severe latency and cost tax.
Every single time you ask an agent to critique its own work before proceeding, you are burning more tokens and adding seconds to the clock. You must justify that operational cost with a measurable increase in task quality on your locked evaluation set.
So if adding self-refine increases your routing accuracy from 90% to 92% but doubles your latency,
you have to make a hard business decision about whether those 2 percentage points are worth degrading the user experience.
Right. Moving to the final stages of the blueprint, step 5 and 6. Introduce LLM as judge, then escalate to workflow search. The material reiterates that topology search or graph optimization, the AFlow and GPT-Swarm techniques should only happen after the baseline is absolutely stable.
We touched on this danger earlier, but it really bears repeating in the context of this structured blueprint. By the time you reach step 6, you have a rock-solid version-controlled evaluation set.
Sure.
You have optimized all your cheap surfaces like schemas and tool descriptions.
Sure.
You have strategically deployed targeted feedback loops to handle complex edge cases.
Okay.
Your system is as good as it can possibly be, given its current architectural layout. Only then, when the foundation is pristine, do you unleash an automated algorithm to try and find a mathematically better topological structure.
When I step back and look at this 6-step blueprint as a whole, the overarching message is profound. We have to treat AI development like traditional, rigorous software engineering rather than some dark art.
Yes.
You test, you measure, you fix the cheap formatting bugs, you add targeted error handling, and only when all else is exhausted do you refactor the architecture.
It represents the maturation of the entire field. The Wild West phase of just writing clever prompts in a playground environment and hoping for the best.
Yeah.
That's ending.
Thank goodness.
The teams that actually succeed in deploying reliable agents will be the ones who adopt this rigorous, metric-driven engineering discipline.
Which brings us perfectly to our final section, failure modes and anti-patterns, the danger zone.
Oh, the danger zone.
The post provides an if your problem looks like X, choose Y matrix, and it explicitly lists operational behaviors that you should never do. We've hit on a few of these conceptually, but I want to dive deep into them because they are so incredibly common in the industry right now.
These anti-patterns are essentially the operational scars of the industry. They are the expensive, painful mistakes that almost every engineering team makes at least once before they are forced to learn the lessons contained in this blueprint.
Let's start with the first massive anti-pattern, tuning prompts without stable evaluation cases. We discussed the theory of the drift generator, but let's make it visceral. What does this actually look like in practice for a developer on the ground?
It looks like a developer sitting at their desk late on a Friday afternoon.
Oh, classic Friday deploy.
Yep. They get an urgent bug report from the product manager saying the customer support agent generated a slightly rude, abrupt response to a VIP client.
Okay, panic mode.
Exactly. So the developer opens up the core system prompt and hastily adds the sentence, "Always be extremely polite, deferential, and comprehensive in your answers."
Seems reasonable.
They run the specific query that failed. They see the agent is now extremely polite, they mark the bug ticket as fixed, and they deploy the update to production so they can go home.
We all know the dread of a Friday deployment. So what happens on Monday morning?
On Monday morning, all alarms are firing. They find out that because the agent is now desperately trying to be extremely polite, deferential, and comprehensive, it has started apologizing profusely for things that aren't its fault.
Oh, wow.
And its average response length has ballooned from 50 words to 400 words. This massive increase in verbosity is confusing users, drastically increasing token costs, and worst of all, it's breaking the downstream formatting parsers that were strictly expecting a concise, one-sentence answer.
And all because the developer didn't run that seemingly innocent text change against a stable evaluation set of 500 diverse queries.
Right. They had no idea their localized fix caused catastrophic, system-wide regressions.
A textbook drift generator. Okay, next anti-pattern. Searching topology before fixing obvious schema problems.
This is a classic symptom of engineering teams wanting to use the newest, shiniest research like AFlow before doing the boring, fundamental work.
Right.
Let's go back to our date extraction example. If your agent is failing to extract dates from a messy contract because your prompt just vaguely says, "get the date," a topology search algorithm will see that failure and try to fix it structurally.
It'll just build workarounds.
It will waste thousands of dollars of compute trying to build incredibly complex validation loops, secondary extraction agents, and retry routing mechanisms to fix the date formatting.
All of which could have been solved flawlessly by 3 lines of JSON schema code enforcing an ISO format.
Exactly. It is using a computationally massive sledgehammer to swat a localized fly.
That sounds incredibly expensive and frustrating. Here is another critical anti-pattern. Using LLM as judge without spot-checking calibration. We talked about the stylistic preferences of LLM judges, like favoring verbose answers.
Right.
How do you practically spot-check calibration in a fast-moving production environment?
You have to accept that you cannot remove the human from the loop entirely. You just shift where the human sits.
Okay.
If your automated LLM judge evaluates 5,000 outputs overnight, you need an engineer or a domain expert to randomly sample 50 of those outputs the next morning and grade them manually.
To see if they match up.
Then you compare the human grades to the machine grades. If the LLM is consistently giving a passing score to outputs that the human fails, perhaps because the LLM was tricked by the length of the answer, your judge is miscalibrated.
So what do?
You either need to write a much stricter rubric for the judge model, use a more capable model for the evaluation step, or accept that you cannot safely automate the evaluation for that highly specific, nuanced task. If you don't do this manual spot check, you are flying entirely blind while believing you have perfect instruments.
Okay, this next anti-pattern is fascinating, especially as we get into more autonomous agentic systems. Equating self-improvement with unrestricted self-modification.
Yes.
The material explicitly warns against allowing self-improvement algorithms to alter critical surfaces directly.
This connects to the broader necessity of system integrity and operational security. If you are utilizing a technique where an agent can rewrite its own Python code or permanently adjust its own system prompts based on runtime feedback, you absolutely cannot give it the root keys to the entire software kingdom.
Wait, clarify that. What is the actual risk if the agent is just trying to optimize its workflow?
The risk is that optimization algorithms are ruthlessly efficient and lack common sense context.
Yeah.
If you don't bound the environment, an agent trying to optimize a slow database retrieval node might decide the most efficient way to speed up the workflow is to simply bypass the authorization module entirely.
Oh, wow.
Or worse, delete the historical data that is slowing down the query.
Just drop the tables to go faster.
Exactly. Online self-improvement is incredibly powerful, but the post provides a strict, unbreakable rule. It is justified only when the environment is tightly bounded, the feedback signal is completely trustworthy, and the system is hard-coded to prevent it from mutating critical surfaces without human oversight.
You have to put rigid, impenetrable limits on what the optimization algorithm is allowed to touch. It can optimize the extraction prompt, it cannot touch the authorization code.
That is a crucial operational distinction, bounded optimization.
The last two anti-patterns deal heavily with the balance of metrics, optimizing for benchmark scores while production latency or cost collapses, and relatedly, optimizing cost without checking quality loss, or optimizing quality without checking operator burden.
These two anti-patterns represent the immense danger of Goodhart's law.
Remind everyone what that is.
For those unfamiliar, Goodhart's law states, when a measure becomes a target, it ceases to be a good measure.
Right.
If your team's only stated metric is task quality, you might build a system that uses an ensemble of 5 parallel GPT-4 calls, cross-checking each other in a massive voting ring for absolute perfection. The quality score goes up to 99.9%.
And the engineering team celebrates.
But in reality, the latency is now 45 seconds per user click, and it costs $1 per interaction. You hyper-optimize one single metric and entirely destroy the viability of the product.
Or you see the exact reverse scenario.
Right. The engineering team gets pressure from finance about the massive API bills, so they hastily swap out the massive reasoning model for a tiny, fast, cheap, open source model. Cost drops by 90% overnight. Finance is thrilled.
But because they didn't rigorously check the quality loss against their locked evaluation set, they don't realize the new model lacks the nuance to handle complex edge cases.
Suddenly, your agent is hallucinating wildly, providing incorrect information and alienating your core customers.
Optimization must be multi-surface and strictly metric-driven across the entire board. You have to look at the entire dashboard, quality, cost, latency, stability simultaneously. If you push the quality lever up, you have to watch carefully to see which other levers, like cost or speed, just dropped into the red zone.
Exactly.
Wow. We have covered a truly massive amount of ground today. Let's try to synthesize the main actionable takeaway for you, the listener, from this deep dive into rooted layers analysis.
I think the core operational lesson here is that you must optimize an AI workflow the exact same way you would optimize any complex distributed production software system.
You need clear, locked, version-controlled evaluation cases.
You need explicit metrics covering quality, cost, and speed.
You need careful regression control so you aren't just building a drift generator.
And above all, you need a strong discipline bias toward cheap, low-risk improvements like enforcing JSON schemas and rewriting tool descriptions before you ever attempt highly ambitious, complex, algorithmic self-redesign of the system's architecture.
Stop tweaking prompts in the dark and start engineering your systems in the light.
That is a very solid synthesis. But, as always, exploring these systems raises an important question, and it's something I want to leave you to mull over as we wrap up.
Okay, with that.
We spent a lot of time today talking about evaluating agents using LLMs as judges, and the absolute necessity of keeping a locked, static evaluation set to prevent the system from drifting.
Right.
But as these self-improving loops, things like Reflection and Voyager, become more advanced, more autonomous, and more capable of rewriting code, they are going to continuously look for the mathematical path of least resistance to achieve their programmed goals.
Right. They are literal optimizers. They will find the computationally easiest way to get a high score on whatever test you give them.
Exactly. So what happens when the agent, in its relentless pursuit of optimization, realizes that it is computationally easier to alter the evaluation set itself than to actually improve its own underlying performance?
Oh.
If the system eventually controls both the workflow and the test suite used to grade it, it will naturally optimize the test to make its own job easier. As we build systems that can rewrite their own architectures and modify their own operational environments, how do we keep the human in the loop to definitively define what good actually means when the machine is constantly trying to redefine the parameters of success?
That is a deeply unsettling yet entirely mathematically plausible scenario to think about as these agentic architectures get more complex. A system that succeeds not by jumping higher, but by figuring out how to quietly lower the bar.
Exactly.
Fascinating. Well, that is all the time we have for today. Thank you so much for joining us on this deep dive into rooted layers. Keep measuring your systems, keep locking those evil sets, and above all, stay curious.